Chapter 21, Molecular Orbital Theory. Section 21.7, Localized Molecular Orbital Theory. Localized molecular orbitals are MOs concentrated or localized on a single chemical bond or one electron lone pair. For example, each of the two beryllium-hydrogen bonds in beryllium hydride can be described by a localized MO formed between the 1s orbital of one hydrogen atom and a sp orbital of the beryllium atom. Over here we have a hybrid orbital with this kind of shape. The normalized wave function of the two sp hybrid orbitals of beryllium are 1 over the square root of 2. This is the normalization factor times psi of beryllium 2s minus psi of beryllium 2pz. This is one of the two sp hybrid orbitals. The other one is 1 over the square root of 2, which is the normalization factor times the beryllium 2s orbital plus the beryllium 2pz orbital. So both sp orbitals are properly normalized. And over here, those are the shapes. So if we have the interaction between 2s orbital and 2pz orbital, we can mix them in two different ways. One way we have a larger lobe pointing to left, the other way we have a larger lobe pointing to the right. The localized MO wave functions of beryllium hydride are linear combinations of the two sp hybrid orbitals of beryllium and the 1s orbitals of the two hydrogen atoms. So now let's look at this beryllium overlapping with hydrogen A, this beryllium overlapping with hydrogen B. So in this case, we have a MO. We put some weight on the coefficients on the hydrogen A. This is 1s orbital of hydrogen A. And over here we have some weight or molecular orbital coefficients d sub A on this sp orbital of beryllium. For hydrogen B, we can have another sp orbital overlapping with this 1s orbital of hydrogen B. So Ca, Cb, Da, Db are simply molecular orbital coefficients. In localized molecular orbital theory, each of the four carbon-hydrogen bonds in methane CH4 are formed between a hydrogen atom and a sp3 hybrid orbital of carbon. So first, let's look at the sp3 hybrid orbitals. Over here, we can use the 2s orbital, 2px orbital, 2py orbital, and 2pz orbital to make four sp3 hybrid orbitals. And those are normalized. This 1/2 is the normalization factor. So look, we can do a linear combination of these four different orbitals: 2s, 2px, 2py, 2pz. Over here we have plus, 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 and then plus, minus, 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 plus, minus, 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 plus. So these four linear combinations will have this kind of shape with 109.5 degrees between any two lobes. It's 109.5, and this is tetrahedral. Mathematically, the four localized MO wave functions of methane are this. So we have the 1s orbital from hydrogen A overlapping with this sp3 hybrid orbital, and we can have hydrogen B overlapping with another sp3 hybrid orbital, hydrogen C, hydrogen D. Each overlaps with a sp3 hybrid orbital. Again, we have four hybrid orbitals centered on the carbon atom. They are four sp3 hybrid orbitals. They can all overlap with one hydrogen atom. So over here you can see overlapping with hydrogen A, hydrogen B, hydrogen C, and hydrogen D. So what are those C sub A, C sub B, C sub C, C sub D, and also D sub A, D sub B, D sub C, D? They are called molecular orbital coefficients. In this case, we're looking at localized MOs, so those are localized molecular orbital coefficients.